Welcome to the course Business Analytics and Data Mining Modeling using R. So in previous few lectures we have been discussing logistic regression. So in previous lecture we were doing a modeling exercise using flight details data set. So let's go back to that exercise in our environment. So we have been able to build the model, right, and we understood, we also discussed the results and different alternative models that could be created by dropping few variables and merging few categories. So we would be doing that, but before that we would like to check the performance of this model, look at some of the plots and discuss them. So first we would like to check the performance of training partition itself. So we have fitted values with us. So fitted values are nothing but the probability, estimated probabilities values for all the observation that we used in previous lecture. So same model result we are using again here in this particular lecture. So first we will use these fitted values to classify observations. So we can see if fitted value, that is estimated probabilities value, if they get greater than 0.5 then the class is 1 and otherwise 0. 1 means here delayed flight. So let's run this. So we will have the classification, and once that is there we can create our classification matrix. So actual value is stored here, flight status, and the predicted value is in just now we have computed. So let's look at the classification matrix. So you can see in the diagonal element 46 plus 20, so these are the observations correctly classified, 46 and 20. And we can also see that off diagonal elements 18 and 12, so these are the incorrectly classified observations. So let's look at the classification accuracy. So this comes out to be 0.6875, so 68.75% accuracy. So this is still good enough, reason being we had very small sample size and even smaller sample size for training partition, and then there are so many factor variables. So therefore there can be so many combinations of values which might not be modeled or which might not have enough number of observations to have a good model. So still we got 68.75% accuracy. This is the error. Now we can look at performance of our model on the 10% observation that we had left out in the test partition. So let's look at the performance. So first let's score the partition for probabilities value. So we will have this. So this is scored. Then let's also score the logit values, and then let's classify these observations. So once this is done, let's generate the classification matrix. So this is the classification matrix. We had just about 11 observations. So 3 plus 2, 5 observations have been correctly classified, and the remaining observations 6 have been incorrectly classified. So our model doesn't seem to be performing well on new data. So just 45%. So that is expected also from training partition to testing partition. Performance might drop down, specifically in this case because we had very small sample size and too many factor variables, right. So as we have talked about in some of the initial lectures, when we talk about factor variables, it is the number of categories that also play a role in terms of determining the minimum number of sample observations, sample points that we should have. So if you have too many factor variables and with quite a few number of categories, then that puts a more higher restriction on sample size. So this is our error. So error is much higher in test partition. So let's look at the lift curve in terms. So we would like to understand, even though the model is not performing as well as we would expect because of the issues that we discussed, sample size and others. Still in terms of identifying the most probable ones, most likely flights which are going to be delayed, lift curve can give us some important information how this particular model is going to help us with respect to an average case scenario. So as we have been doing for plotting cumulative lift curve, first we create this data frame where we have first column we have probabilities values, and then the second column we have typically the actual class. So let's create this. Let's look at first 6 observations. So we can see that these are the values. So this is for test partition. We have total 11 observations only, and once this is done, we would like to sort this particular data frame with using actual class variable and decreasing order. So the code is written there. Let's look at the sorted values. So these are the sorted values. The data frame has been sorted with respect to probabilities values, with respect to probabilities value, descending decreasing probabilities values, descending order. And now we will compute the cumulative class, and let's look at the cumulative class variable, this data frame. You can see, so this kind of exercise we have done before as well. Now let's create the cumulative lift curve. Let's look at the range. So this is the range. So as I said, we have just 11 observations, and this is the range for cumulative actual class. So out of 11, probably we have just 7 observations belonging to delayed class category. So let's create the plot. We need to correct our limits first. So let's make it 8, and other things seem to be okay. So now let's run again. So this is our plot. Let's create the reference line. Reference line can further be corrected here. As we can see, first record cumulative actual class is 1. So this reference line can actually be 1 and 1. So this would be a much corrected version, improved version of reference line. For this we will have to create a plot once again, then reference line, and then we can add the legend. So this is the plot that we have. So you can see that the lift curve goes below reference line somewhere here, but again it picks up. So but in this starting region, you can see for most part of this particular lift curve, this solid line, which is for our model, remains above this reference line. That means our model does a better job of identifying the most probable delayed flights with respect to the reference case, that is average case. So now what we have understood from this exercise and the results that we had discussed, we can go ahead and do a remodeling of this particular data set, this particular problem, delayed flights prediction problem. So let's look at the logistic regression results once again. So as we can see that from in these results that 3 variables were found to be significant. Flight carrier, this is significant, specifically this indigo dummy variable, and then source is also significant, one of the dummy variable is significant. Destination also one of the dummy variable is significant, right? Day is however this is not significant, but this could be of practical importance. Reason being, even though in our small data set that we just have flights on 2 days, Sunday and Monday. However, on working days the schedule might be more traffic might be more flights might be running during working days. So therefore and in comparison to weekends, so therefore this particular variable day is important information. So because of its practical importance, we would like to keep it despite it being insignificant in our small data set and model. Distance doesn't seem to be significant, it is highly insignificant. So probably it's not an important point, because anyway the flights the jets that are used, they fly at a quite good speed, so distance is not a matter. It's the operational factors which matter more. Flight time, of course, can be important, because flight time, if the flight is time is more, then there are more chances for some factor playing a role, more like some factor playing a role in terms of delaying the flight. So flight time we would like to keep, and also you can see that p value is on the lower side. So by a small margin, this has been otherwise it would have been significant at 90% confidence interval. So it has been left out by small margin. Departure intervals also, because of the practical importance, we would like to keep it, because flights, at what time the flights are originating or arriving, so that can play an important role in terms of whether the flight is going to be delayed or not. However, we would like to look at the categories. We would like to find out the categories, use the categories which would give us more some improvement in our classification model. So from this probably it seems that the departure, this one 18 to 24 category, with respect to reference, if we look at the p value is smaller, so probably we look to combine these two categories, the reference category and this departure 18 to 24, and the other two categories will group into one, departure 6 to 12 and 12 to 18 we would like to group into one. So that we can call day, and the other categories 18 to 24 and then 24 to 6 that we would like to keep at the reference category. 0 to 6 we would like to keep as night, part of night group. So two categories will be part of day group, two categories will be part of night group, and we will like to see how it is performing in the model. So let's open. Start our modeling exercise. So before, let's clear some of these variables and data frames from the environment section, because that might create some problem in this particular code. So what we will do, so this library is already loaded, so we would like to again import the data set. Let's remove any row, any columns, any rows, first 6 observations, structure. So this we all have already gone through in previous lecture. Let's take a backup. Let's change the time so that it is in appropriate format for us to derive some variables like we did in previous lecture. So these are the observations. Now here we do certain variable transformation differently based on our learning from previous modeling. So as you can see that range is of course going to remain same, but now the grouping that we are going to do, the categories, the groups that we are going to create for departure time interval are different. Now we would like to, as we discussed, we would like to create these two groups, day and night. So all the flights which fly from 6 to 18 hours, so that would be categorized as day, that would be grouped as day, and remaining flights would be grouped as night. So we can have a few other changes. So we don't have to, we should not be restricting ourselves to this particular time 6 and 18, and this can be changed depending on how useful it in terms of predicting delayed flights. So we have to keep working on these categories and how they are created. So for this model we will go with these hours 6 to 18 and then remaining as another group. So we are using if else to perform this categorization. So once it is done, will you can see in the environment section a character vector has been created for all observation specifying whether it's a night flight or day flight. So let's add this to our data frame. Now we would like to convert it into a factor variable. So let's do that. Day we would like to, as we discussed, we would like to include this in our model, though it was found to be insignificant because of the practical importance. So let's convert it into factor variable as well. The labels, as we did in previous lecture, labels for day would also, we would like to change from 1 and 2 to Sunday and Monday. And flight time, as we discussed, this is also of practical importance, so therefore we would like to have it in our model. And as we did in previous lecture, we use as dot diff time to convert the particular values for this variable into a suitable format. So these are the values. So some of the convergence transformation we have performed. Let's look at the first 6 observations. You can see flight time appropriately mentioned. We still have some of the variables that we would we will be taking subset. So before that, let's take a backup of this data frame. Now you would see that we are getting rid of column number 1, that is flight number, then column number 3, that is date, so we don't want it, then 5 to 8, that is scheduled time of departure, actual time of departure, scheduled time of arrival, actual time of arrival, like the previous model. So we get rid of these variables as well. Then the next one is 10th variable, that is the next one is 10th variable, so that is day, that is day. Also, as we saw that even though this is of practical importance, we are not including this on our model because this was insignificant. So we will see how it what the results would be once we exclude it. So this is also gone. And then we have distance. So distance also we are trying to get rid of. So these variables will get rid of. So now these are the remaining variables. We have flight carrier, 3 labels. We have source, destination, 3 labels. Flight status, we will have to correct the labels as we did in previous modeling, previous lecture. Flight time is okay, and departure. Now we have just 2 labels, day and night. So let's look at the first 6 observations. So these are the observations. Now let's work on the outcome variable. So we'll go through the same piece of code that we did in previous lecture. We would like to change the labels, delayed and on time. So as we said, because we generally typically create cumulative lift curve, and for that we require this particular variable into 0 and 1 format, numeric code format, so that we are able to later on do certain computations. So we would like to change this. You can see delayed is 1 and on time is 0, and now we would like to relabel it so that the reference category is 0. So let's execute this. So now reference category is 0, as you can see. First 6 observations also you can see. Now partitioning is same, 90% for training partition because of the smaller sample size. So again in this modeling exercise also we would like to follow the same. So 90% and 10% for the testing partition. So once this is done, let's create the model. So model all the arguments remain same, so there is hardly any change with respect to model. Let's look at the results. Yes, so now if we look at the results, now the level of significance has gone up, right? So you can see the flight time, this is now significant at 2-star level. That means it is significant at 99% confidence interval. That is flight time, because so this could be because we have this smaller sample size, and this time the observations that have been selected for that to be part of training partition, that will also have their influence because of this smaller sample size. And you can see flight time is significant at 99% confidence level, right? So so this is one change. So in the last modeling, this was this was just left out by a small margin to achieve the significance at 90% confidence interval, right? So another important source. So in the previous modeling we saw that Madras dummy variable for source, so that was significant at 90% confidence interval. Now this time it is significant at 95% confidence interval, 1-star level significance. Now we can see that destination, the same dummy variable which was significant last time, also is significant at 90% confidence interval. So there is no change in confidence interval for this one. Now there is one change. We can see that in this time our flight carrier, the Indigo dummy variable, which was significant at 90% confidence interval in previous model, now this has missed by a bit more margin for 90% level significance. However, because of the practical importance and even if some of these variables are insignificant, we would like to use them in our modeling, in our predicting and in our predictions, right, scoring new observations. So if we look at the last variable, that is departure interval night, in this case this doesn't seem to be significant, right. So it seems that either we will have to work further on departure time intervals to understand if there is any difference between two groups of intervals. However, we have tried in previous modeling, we had created 4 groups, and in this particular modeling we have created 2 groups. So this also underscores the importance of descriptive analysis. So probably we should focus more on this particular grouping in our pivot table descriptive analysis to find out which groups, if there are any groups which can be created with respect to prediction of delayed flights, classification of delayed flights. So another variable, this destination airport, we have already discussed other variables. So now let's look at the performance of some of this model. So measures of goodness of fit can also be computed. So discussion on this we'll do later. So however, if you are interested in seeing the values, so these are some of the values that could be interesting for a different discussion. So these are some of the observations. Multiple R square is quite low for this model, 17%. So that is another reason for low performance of the models in previous exercise and maybe in this exercise as well. So let's look at the performance. So from the low R square value, we can say one thing, that probably we need to think about more variables which can increase a certain R square, which can increase R square to by certain margin. So let's look at the performance of training partition itself. So mod fitted values we have. So these are estimated probabilities value. Let's classify the training partition observations. Let's look at the classification matrix. So you can see 44 plus 24, these are the observation correctly classified. 17 and 11, so these are the observation incorrectly classified. So despite low R square value and many variables being insignificant, however, because they are practically, because most of the variables are of practical importance, we can see that the performance for training partition is 70%, 70.8. If you remember the performance of previous model that we had, that was around 68%, this is around 70%, more than 70%. So there is 2% increase after certain transformation of certain modeling that we did this time. So you would see that is this particular modeling exercise, these 2 models that we have created and looked at the performance underscore some important points. For example, when we talk about data mining modeling, when we talk about prediction task, classification task, even if some variables are not insignificant, but if they are of practical importance, that can help us in predicting new observations. That is quite clear from the performance numbers as well. However, we can always work on certain variables, specifically factor variables and the transformation regrouping that can be done and improve our performance further. So error is despite a small sample size, so we got this much performance. Now let's look at the performance on test partition. So we have this till 11 variables, I think, like the last time. Yes, 11 variables in the test partition. So let's see the performance. The outcome variable we would like to leave out. So let's look at the 1, 2 3 4, yes, so correctly specified, so it was the fourth column, so we would like to exclude it for the clarity. So probabilities values are estimated, logit values are also extracted, and let's classify the observations. Let's look at the classification matrix for test partition. So we can see that 6 plus 2 are the observation correctly classified, and 2 plus 1, that are these are the observation incorrectly classified. So the model seems to be doing a good job this time. However, this, as I would like to point out, however, this is because of the way partitioning might happen. The observation that go into training and the remaining observation that are left in as part of test partition. So because of this, there are going to be certain swings in performance. So therefore, what we require is larger sample size, and within that we require larger number of observations to be part of training partition, and therefore check the performance on test partition. You can see in this particular case the performance of model is better in test partition, which is not always expected. So in this case it is performing well. Now what we will do, we will also look at the lift curve this time. So let's see how our model is doing in terms of identifying the most probable delayed flights. So as we did in previous exercises as well, let's create a data frame of probabilities, values and actual class. So this is for training partition. So let's create this. So these are the observations, probabilities, values and actual corresponding actual class for those observations. Let's order them, sort them with respect to probabilities, values, decreasing order. You can see first observation is having highest probability value and the corresponding actual class. Now let's compute the cumulative actual class numbers, that column. Let's add it. Let's look at the observations. So once we have this information, let's look at the range and create. Let's look at the range now. Let's create the cumulative lift curve. So we can see x limit and y limit, they seem to be okay, 1 to 96, and that is covered, and y limit also 1 to 45, this here we have 0 to 45, so this is covered. So we can go ahead and create our plots. For the reference category, in this case this should be 1 and 1, so we will get better reference line this time. So this is our reference line, and let's insert the legend as well. So let's look at the cumulative lift curve. So as we can see that in majority part of the reference line, the model curve remains above the reference line, and so that indicates that usefulness of the model. So as we have talked about that sometimes our model might be giving might not be giving much improved performance in comparison to reference case, typically because of the sample size problems. However, even with those smaller sample size, in terms of identifying the most probable ones, the model does a better job. So you can see that in terms of identifying most probable ones, the model always remains above this and does a better job. So as we discussed in the previous lecture, we are always looking to we are always interested in top left corner of this particular curve, right? We would like to identify as many observations correctly as possible. So probably somewhere here. Let's create cumulative left curve for our test partition. So first let's create this data frame, probabilities, values and actual class. First 6 observations, let's sort them out, decreasing order of probabilities, values. So we can see here the same. Let's compute the cumulative actual class values. As you can see, now in this case for reference line, we can see it should be 1 record and 0 value, so that has to be reflected there. Let's look at the range again for the test partition. So a range for x limit is appropriate, for y we have to change, that is also appropriate. So let's create this curve. So this is the curve. So because there are very few observations that we have in test partition, so that could be curve might sometimes be touching the reference line or even going below. Reference line first coordinate should be 1 and 0, so that is fine. So we can create our reference line. Let's create a legend. So as we can see, because few observations, therefore some part of this particular plot, we can see that model is going below the reference line. However, initial part of the plot, we can see the model is clearly above the average case. This is for very small, just 11 observations in test partition. So again, here we can say usefulness of the model is that we can easily identify, it is does a much better job of identifying the most probable ones. So with this, till now in logistic regression modeling, we have done 2 exercises. One was using promotional offers data set, and then this one was using this applied detailed data set. Some of the important points like goodness of fit measures, because logistic regression is a classical statistical technique and it is quite popular, as we talked about in statistical modeling. In the next lecture we'll also discuss some of those aspects, with respect to the statistical modeling. We'll build a few more models which could be more useful for a classical setting. We'll also try to understand the difference between logistic regression and linear regression, where we look at why linear regression is not suitable when our outcome variable is categorical in nature. So we'll discuss those points as well. We'll also one particular task that we discussed in our previous logistic regression lectures, that logistic modeling can also be used for profiling in terms of understanding the similarities and differences between two groups. So how it can help, how logistic regression model can help us in profiling tasks, that also we would like to understand. So some of these things we would like to do in we will be doing in next lecture. So at this point we will stop. Thank you.